Alright, I'm back. Right now, it's April something? I don't know. Yeah, I had planned to finish it, but I hadn't, now. I was actually planning to do this video a long time. I mean, it is quintessential for Diffgeo and stuff. It's just Fanatic decided to do his own videos, so whatever. Yeah, so, I'm also gonna use my notes here, because, I can't really remember this shit. So, yeah. My notes are great, though. So, yeah. We were on vectors, right? So, we know that the derivation the derivation of a function, right? Say we have a function mapping u, which is a subset of Rn to R, right? A real valued function, right? This is going to be equal to the limit as t approaches 0 of f of c of t minus f of t, I believe, over t, right? Which is just going to be the derivative of d dt t equals 0. Hold up. That don't make sense, dog. That don't make sense at all. Alright, I guess it does. Oh yeah, t equals 0 of f of c of t. Right. Hold on, let me throw this away. Actually, I don't need to throw this away, but I will get a new marker because I do not like this marker for videos. It's not good for videos. Right. So that's just, and c of t, of course, is going to be equal to p1 plus tv1 pn plus tn tvn. And also, I hope you know that I didn't mean to section this video into two parts. I'm just too lazy to edit. Time for race. I'm in a race of time, and I made a mistake on the second part of the video, so yeah. Okay, so that we know that this is the directional derivative at a vector v, right, of a function, right? Yeah, at a specific vector. This is the direction vector and this is the function, right? And this can also be represented. Let me see where we're going with this. I've not picked up this in a week, so yeah, remind me. Okay, which is also just going to be equal to, as you know in Calculus 3, the gradient of f dotted with the direction vector, right? Which is actually just going to be equal to each component, the sum of each component, and the partial derivative respect to I of f p, right? X of I is going to be the standard coordinates, right, on Rn, right? X of 1 all the way to x of n. Those are the standard Euclidean coordinates, right? So, really though, we can also represent, we'll call this the direction, the derivation, right? This could be equal to v of I, partial derivative of I of x of p, right? This is where more of the canceling out comes to fruition. Okay, so next I'm going to kind of go over and generalize this, right? More in terms of mappings, right? So I'm going to define what a germ is. So we, first of all, define germ by defining an equivalence relation, right? With this equivalence relation. Say this maps certain neighborhood around P, right? An open neighborhood around P of Rn to R. And then this also maps in a different open neighborhood around V of Rn to R. So they are both real valued functions over some open neighborhood of P, right? And we say that they are equivalent if and only if their inputs at the intersection of both the neighborhoods are the same, right? And we call these germs, right? And we call the set of all germs of Rn, we denote it by this, at some neighborhood of P, right? Oh yeah, they're also smooth, as indicated by this. They're both smooth, real valued functions, right? And we denote the set of all germs around a neighborhood of P in Rn by this. Yeah, it's a mouthful, but just kind of recall that. So really, now we can define. We can define the derivation at a point as a mapping of a set of germs at P to R, right? Without Rn being defined, right? It could be Rm, R, etc. And this is actually an R linear mapping, right? We call it R linear mapping, which is a lot like a homomorphism, right? So, in this case, what we mean by R linear is that algebra is preserved, right? So it satisfies these properties. It preserves addition, and you could probably see what I mean by preserve for the inputs, right? And it also preserves scalar multiplication. So it's a lot like a tensor or a linear mapping. It is linear mapping. C DV R. And it also satisfies the Leibniz rule or the product rule, right? And hopefully you know what the product rule is. I'll just kind of put it down. F dot G, which is equal to D of F G plus F dV of G. Right? This is what we'll just call the Leibniz rule. I don't know how to pronounce it. Leibniz rule. Just, yeah. Okay. And we'll denote the set of all possible derivations at P, right, without like a specific vector, right, by this, a calligraphic D, right. Set of all derivations at P, right, over Rn, right. Yeah, and of course, without a specific V, so it takes in all the types of V, right? Now, this is where it gets interesting, right? This is really why we kind of defined all that mumbo jumbo, because we can actually build a function between, right, the tangent space of P, at P of Rn to the set of all derivations at P of Rn, right? Which is just going to be a mapping from V to dV, right? First of all, we can easily show that this is a linear mapping. So we have V plus U, right? That's going to map itself into d of V plus U, which is just going to be equal to d of V plus d of U. Right? We can see this basically being equal to and this is obviously so, right? And we can also see scalar multiplication working. We multiply CV, and we get, this is going to be equal to C of dV, right? So it's a linear mapping, first of all. Secondly, so a linear mapping basically makes it a homomorphism, right? Secondly, it's a bijective mapping, which makes it an isomorphism. First of all, we're going to prove why it's it's an isomorphism, right? So, first of all, we prove injectivity, right? Oh, fuck. I forgot which one. Fuck, I keep forgetting which one's injective. Oh, yeah. Oh, yeah. Which basically says that if f of x, or, okay, in this case, if f of u is equal to, or yes, phi of u is equal to phi of v, this implies that v and u must be equal, right? This is injectivity, right? So really though, since this is a homomorphism, right, we can just prove, right, that if we could say that if this is equal to 0, right, suppose we have a case where this is equal to 0, this must imply that v is equal to 0. Why is this so? Because, right, if we subtract these two, this is equal to 0, right? Which is actually, well, so first of all, we start off with f of x is equal to f of y. I'm not looking at this, I'm just saying any homomorphism, right? Or linear mapping, right? Then we can also extend this to f minus fy is equal to 0. So then, since this is a linear mapping, we can say that this is just equal to f of x minus y, which is equal to 0. We find the inverse of 0, which is going to be equal to x minus y, right? So then this implies that this must be 0, so x must be equal to y, right? So that's all we need to show now, okay? To prove injectivity. Yeah, so 0 is equal to d of v. And for the input, we'll use the some coordinate function x to the j. I mean, not x to the j, but xj, some random j, right? Which is then going to be equal to sum of v of I, partial derivative of xi, x of j, right? Which is then just going to be equal to v of j, right? Because this is really, yeah, this is v of j. Because if it's not anything else, yeah, if I is not, there we go. If I is not equal to j, this is just going to be equal to 0, right? Right? Because any partial derivative, we take the partial derivative like of with respect to x of y, this is just going to be equal to 0, right? We know that. So then this will just, everything will be 0 except when this is j, which then this will just be 1, right? So then this must be equal to v of j, so then this implies that v of j is equal to 0. And we've proved that this is injective, right? I'm going to get into the intuition later. This theorem, right, there's a lot to unpack. So I'm going to, this theorem applies a lot and stuff. I'm going to get into the intuition later, and first of all, I think everybody should, have the proof and stuff. I usually don't do proofs because I think they're stupid and you could just read a book for proof, but in this case I feel like it's quintessential to get the intuition. And also I just look like